Hi there, in this lecture we're going to be talking about range images as a basic 3D modality that can be used for learning. In this lecture we're going to touch the following topics. We're going to talk about range images as a basic 3D modality and describe their properties. Then two external paragraphs will be representing the moving scene and perspective projection. And then we will talk about how we can actually form dense range images to model the geometry of the 3D scene artificially using raycasting. We will further learn with describe how we can learn with dense range images and touch the cases of single depth image in the context of processing depth images for super resolution and smoothing, and also focus on learning with multiple depth images. We start with viewing range images as a basic 3D modality. As you have already understood from the previous lectures, range images are resulting from 3D scanning. Many of the range scanners are designed to return range images as organized in a 2D representations. To this extent, range images are basically the raw output of a large number of 3D sensors, including laser stripes, structured light setups, and time-of-flight cameras. They are also the result of the state-of-the-art multi-view stereo matching methods, such as binocular stereo or active stereo, and also shape from focus or defocus, and so on. To this end, dense 2D range images are arguably the most frequently obtained data modality. Let's view some of the types and the properties of range images. In the literature on range image processing, the term depth denotes three different types of range data. It's either orthogonal depth, where the depth corresponds to the distance from a point in the 3D scene to the image plane. Perspective depth, where the distance from a point to the 3D space, in the 3D space to the camera is being considered. And disparity, which in fact denotes the difference in image locations of a feature within two stereo images. To this end, orthogonal or perspective depth really represent metric depth, while disparity is the difference in pixels in the image space that is inversely proportional to depth. Basic properties of range images are their comparatively low resolution and high amounts of noise and outliers compared to RGB photo images. For instance, Intel RealSense D435, which is a real-time active stereo described in the previous lecture, is able to capture depth at only VGA resolution of 640 by 480, while RGB images are being captured at full HD, nearly 2 megapixel resolution. The same is correct for Microsoft Kinect version 2, which is a different principle of an RGBD camera, but is also able to capture depth at 30 FPS using a projected structured light pattern. It only captures depth at 512 by 424 pixels, while RGB is also captured at nearly 4 times the same resolution. So the question is, can we actually obtain depth at the same spatial resolution as RGB images? Another property of depth images are their higher amount of noise and outliers, or relatively low depth accuracy. For example, Microsoft Connect v2 is able to capture depth that is only accurate to 2.5 centimeters at 2 meters distance. Commonly, precision and accuracy are proportional to the depth value, which means that the error in determining the depth generally increases proportional to the measured depth. Moreover, some of the sensors, such as, for example, Intel RealSense, quantizes depth. For example, it uses only 64 different disparity values, which generally means coarser depth estimates as we are moving further away from the sensor. So another question is, can we actually obtain cleaner, more detailed depth images that one can use for different applications such as reconstruction? Paragraph number 2 on representing a moving scene. Please see the links to the video by Professor Kramers that I posted on Canvas. Paragraph number 3 on perspective projection. Please see the links to the videos by Professor Kramers that I posted on Canvas. In the following section, we are going to discuss how we can actually obtain or render 2D images of the 3D objects or scenes in practice. One of the older and earlier approaches to obtaining 2D images from 3D scenes is called raycasting. In a number of applications, for example, visualization or learning with images of 3D shapes, we must use a 3D object and compute or render its 2D image representation. Within the context of this course, we are interested in obtaining 2D range images that describe object geometry as a 2D depth map captured from a particular view. So raycasting that we will describe further is one of the basic techniques which shoots multiple rays in the direction of viewing, computing their intersections with the geometry of the 3D scene. It was proposed by researchers from General Motors in the late 1980s to render solid objects such as blocks and cylinders, but has since then been expanded to virtually any scene geometry. The renderings of shaded and wireframe 3D shapes on this slide were obtained by Scott Roth as early as in 1979. Raycasting method is very simple conceptually. Geometric rays are traced from the eye of the observer to each point in the 3D scene to probe visibility and possibly sample radiance received by that point in the scene. The locations of intersections between the ray and each surface point along its path have to be computed, which then can be used to estimate an image, trace a line drawing, or compute volume of the shape. To generate a depth map of an object, raycasting requires creating an array of 3D vectors representing rays, one per each pixel in the image, drawn according to the chosen projection model. For perspective projection, rays must pass through the center of projection and the center of each pixel. For parallel projection, the rays are perpendicular to the image plane. An intersection between the ray and each surface point along its path must be computed. For graphics applications such as realistic rendering or normal mapping, shading must be computed at the intersection point to end up with the color of the pixel. The most expensive operation performed during raycasting is computing intersections between the rays and a set of surface elements, such as triangles. To efficiently perform this computation, a number of speed-up tricks has been developed over time. We will only study the one useful case, basically ray triangle intersection. To compute a ray triangle intersection, we need to recall how do we actually represent any point in the triangle. Let f of uv be an explicit parameterization of a triangle with vertices a, b, and c. So f of uv is basically the xy coordinate of any point. It's basically parameterized by the normalized internal coordinates in the triangle u and v. In the 3D space, the ray is parameterized explicitly as a point E, which is the origin of the ray, and then we add to it the TD, where the T is a non-negative parameter, and the D is the vector that determines the direction of the ray. The ray intersects the triangle if there exists a triple T, U, and V, such that these two quantities, P of T and F of UV, intersect. So they're actually equal. So it's very easy to solve by yourself to identify the appropriate combination of T, U, and V. The core of a ray tracer, in fact, is its acceleration structure. So imagine a scene with tens of millions of triangles and billions of rays being traced. The brute force approach of testing every ray against every surface element, typically triangles, for intersection is clearly infeasible. One way of speeding up computation of intersections would be to sort triangles into a spatial data structure that guides the rays to potential intersection candidates. A popular acceleration structure known as a bounding volume hierarchy, or BVH, sorts triangles into a hierarchy of boxes, for instance axis-aligned bounding boxes, where each level contains increasingly smaller subsets of the scene. At each level, the set of triangles is split into two or more subsets, until the sets are considered small enough. During raycasting, a ray only needs to be intersected with triangles that are contained in a box that the ray intersects. Due to the hierarchical nature of the data structure, the majority of boxes and triangles can be quickly discarded, reducing the work per ray to a few dozen ray box intersection tests and a few ray triangle intersections. This kind of accelerated structure is used, for example, by the efficient Intel Ambri CPU implementation of raycasting. That is, for example, available in the 3Mesh library and also as a binding PyAmbri for Python. So to sum up, raycasting traces ray from the eye of the observer into the scene and computes intersections locations with the scene geometry, for instance with the triangulated surfaces. To efficiently compute these intersections, it uses accelerated data structures to print parts of geometry. We start by reviewing tasks and properties of single-depth images. During this year in the course, we will not consider technical solutions to improving depth quality in detail, but rather will get familiar with the tasks and fundamental approaches. Most 3D scanners commonly capture both depth and color images of the same scene, storing these as a whole image. Unfortunately, for most methods of depth acquisition, the resolution and quality of the depth component are significantly lower than that of the RGB component. A series of research questions therefore makes sense to ask, all motivated by the inferior qualities of the sensed depth maps. For instance, obtaining depth measurements at the same spatial and pixel resolution as the RGB component, or obtaining higher quality depth maps, meaning noise-free and spatially complete, remains an open problem in depth sensing. Other applications, such as achieving semantic scene segmentation using RGBD data, still remain relevant. Let us briefly review several tasks related to processing of sensed depth images, where learning-based approaches have been extensively applied recently. One such problem is upsampling, or super-resolution. As we have previously noted, both spatial and pixel resolution of the range images remain low due to the nature of acquisition process. Therefore, one of the core tasks of low-level depth sensing is to increase the resolution of the depth image to match or supersede that of the RGB. As there is a high correlation between the geometric features of the color image and the depth map, for instance object edges, it is natural to use the color image to improve the resolution of the depth map. Another relevant task is depth completion, commonly relevant for laser measurements such as LiDAR scans. Commonly, such scanners provide a sparse point cloud which cannot be regarded as a depth image, however, may serve as a sparse set of measurements, supporting the estimation of the denser and complete depth image, which may further be employed for navigation and reconstruction. When the depth maps are used in the 3D reconstruction process, for instance to scan objects for virtual reality applications, the resulting scans are often significantly noisy and quantized in the direction of the camera. This is due to either the depth acquisition algorithm, which might aim to only reconstruct a fixed set of disparity values, or, for instance, due to suboptimal lighting conditions. The goal of depth denoising or enhancement is to accept a low-quality depth map and produce its denoised version by smoothing and interpolating raw sensed depth values. The resolution of the depth map does not necessarily get changed. Let us consider a number of properties related to this problem. We will take depth super-resolution task as an example, however, the presented reasoning applies to all mentioned problems. Depth map super-resolution is a non-trivial task. For instance, find structures that exist in a high-resolution image are either lost or severely distorted depending on the scale factor used in low-resolution image because they cannot be fully represented by the limited spatial resolution. A brute force upsampling of low-resolution image simply causes those structures which are supposed to have sharp boundaries become blurred in the upsampling image. Ambiguity in super-resolving the severely distorted fine structures often exists, especially for the case of single-image upsampling. As we observe, depth map mainly contains smooth regions separated by a small amount of edges. Unlike color image, depth map does not have too much texture information, and what really affects the depth quality is the sharpness of depth edges. However, there is a high correlation between the geometric features of the color image and the depth map, for instance object edges. Thus, it is natural to use the color image to improve the resolution of the depth map. The goal is to establish a correspondence between an intensity edge and a depth edge. Since the intensity image is at a higher resolution, its intensity discontinuities can be used to locate the associated depth discontinuities in a higher resolution. although there could be an exception that the intensity edge does not correspond to a depth edge or vice versa. The corresponding assumption has been widely used in the literature. Therefore, locating depth edges precisely is more important to directly infer the depth value of each pixel. So, some approaches focus on learning a binary edge map like the one shown on the right, that indicates the location of depth boundaries from the low-resolution depth map and the corresponding color image. Intensity image corresponding to depth is often used to guide the upsampling process or enhance the low-quality depth maps. However, one would encounter issues too in exploiting the intensity guidance. The variation of depth structures in the depth image may not be consistent with that of the intensity structures in color image, as they are different in nature. Using image-guided filtering, features in intensity images are often over-transferred to the depth image at the boundaries between textured and homogeneous regions. To this end, we need to develop methods that are capable of recognizing features in the RGB image that must not be transferred to the super-resolved depth. A critical aspect of any upsampling method is the measure of quality it optimizes, that is, the loss function. Most existing research on depth super-resolution is dominated by simple measures based on the direct comparison of point-wise depth values, for example, root mean square error between two depth maps. However, the point-wise difference in depth does not capture the visual difference between two similar 3D shapes at a given location. Perceptually based distance measures have been studied in the context of super-resolution of RGB images. For instance, in the lower figure in the slide, the central reference image has been modified twice. First, by slightly increasing its brightness, which leads to a brighter version presented on the left, and second, by blurring the image, resulting in the version of the right. The counterintuitive result is that the brighter version is farther from the reference in a pixel-wise sense than the blurred version. This disagrees with human judgments. Visual similarity measures aim to be consistent with the human judgment, for example, in the sense of similarity ordering. The question asked here is which of the two presented images more closely resembles the reference image. To remedy this disagreement, one way is to replace a common pixel-wise distance loss function by a visual distance function. To this end, one needs to remember that the depth maps really represent a 3D surface. One may render the respective surface and obtain the visualization in the form of a grayscale intensity image. Observe how two surface visualizations on the right are entirely different in terms of their quality, while the respective depth images in pseudocolor are almost identical perceptually. Attractive properties of these visualizations are that they can be computed using surface normals only, while allowing to apply structural image similarity measures, such as those based on simple vision models of structural similarity, or low-level visual processing in the human brain, or perceptually based metrics produced by neural nets. To build depth processing algorithms, a variety of different RGBD images are available, ranging from simple and clean synthetic data to the lowest quality real data. These are presented in the slide along with their respective 3D shape renderings. To recap with an overview of single-depth image processing, we gotta deal with range image acquisition artifacts such as low resolution, holes, or sparsity. However, more conventional tasks such as semantic segmentation and object detection are still relevant. Algorithms that work with depths commonly use RGB intensity image because they have higher resolution and lower amounts of noise. One way to enhance depth, super resolution, and completion and enhancement could be to incorporate a visual similarity assessment measure in the training process. Let us switch to considering depth images coming from multiple views. In most sceneSee tabs, range images are acquired from different, generally intersecting views, where they are able to provide complementary contexts. Acquiring RGBD videos is furthermore a built-in feature in most RGBD cameras, such as Intel RealSense or Microsoft Kinect, and so providing multiple view images is a standard way of providing basically the data in RGBD format. Also, structured light setups, which feature like a turntable, are also delivering a series of depth images like the one depicted in the right-hand side here. So this naturally makes sense to leverage multiple view depth imagery to reconstruct signals defined on surfaces of 3D objects. These include, but are not limited to, feature line extraction, estimating differential quantities such as normals or curvature, shape segmentation, and many others. I will briefly describe a particular task in this area where I have specific experience. However, you can imagine how multiple other tasks can be formulated in the same framework. We start with the recently published collection of geometric CAD models called ABC. These are mostly man-made engineered objects with well-defined surfaces and clean geometry. For 3D CAD models of man-made objects, ABC provides analytic differential quantities such as normals. Some surfaces contain curves, where normals change rapidly in the direction perpendicular to the curve. We display those sharp curves in red on the right. One may build a pipeline to produce collection of training datasets used to infer the location of geometric feature curves from the raw scan data. We start with selecting local regions in the CAD model and the set of its interior geometric feature curves. We can further use raycasting method, for example, to generate a dense 3D image of the local region in the shape. This is going to be a range image, and the 3D measurements sensed in the surface are used to query distances to sharp geometric feature lines. The resulting training samples are represented by pairs of depth and distance field images from multiple viewing directions. The setup just described can be efficiently utilized as a framework for many problems of interest, where the goal is to predict a per-pixel quantity such as the semantic label or a distance field from a dense range image. Convolutional neural nets are a natural fit for this task, as they allow to efficiently utilize dense spatial context and are easily modified to allow additional inputs, such as color images. For ambiguous regions, such as locations with little spatial context, or near shape boundaries, or due to occlusions, one would not generally be able to accurately predict the target value from all views. For instance, one may easily see that in the right figure, predicting per pixel distance to feature field is challenging near the edge of the 3D shape, where not enough context is available, in addition to noisy predictions overall. The question is, can we obtain a coherent set of predictions for the entire 3D shape? So how to combine predictions obtained using multiple individual views? Two common strategies for approaching this task exist. The first one is essentially post-processing, where we're fusing predictions obtained using individual views The second one is slightly more elaborate as it allows to employ multiple view consistency in the scene during training. Essentially, multiple view consistency means that the results obtained in the same global 3D location using individual views must be consistent with each other, that is, approximately the same, where we should also take a validity mask into account. Let us first introduce a number of notations before we proceed further. We will call I sub ref reference depth image and an additional M images that depict views of the same scene as I sub M, where M goes from 1 to M capital. D ref and D sub M are the quantities of interest, for example, distance to feature annotations. We will also assume that we have camera intrinsic parameters that is shared across views, that we're taking images using the same camera, and that we also have a relative intrinsic parameters to transform between E sub ref and E sub M. Let us start by considering a reference view is I sub ref and a pixel U in that view. Its depth value and prediction are related to those obtained from the other views by a simple transformation. First, we obtain 3D coordinates of pixel U in the reference image frame by unprojecting U to 3D using the intrinsic camera parameters. Next, we can compute the 3D point location of the pixel in the global frame to obtain X capital. To figure out how the point X capital is related to a different view I sub M, we use the associated intrinsic and relative extrinsic parameters and warp the reference view to the novel view, obtaining U hat. We follow by using the bilinear sampling to yield I sub M of U hat. So the actual value of the image need resampling on the image grid to obtain an interpolated prediction. Alongside the warped image, a binary validity mask is also generating, indicating valid pixels in the novel view, because some pixels project outside the image boundaries in the novel view. The prediction fusion algorithm then proceeds as follows. As input, we're taking depth images and predictions obtained for each view independently, for instance using a neural network. The goal is to obtain predictions that are consistent or approximately the same across views. So this is what we do. For each pair of views I sub ref and I sub M, so that is the reference and the novel view, we commonly fix the reference view and we iterate over novel views. We compute the novel view pixel coordinates for each pixel in the reference view. That we do the reprojection by unprojecting from the reference view through the 3D space to the novel view. We compute an interpolated prediction in the pixel space by basically sampling the predictions obtained for the novel view using linear interpolation in the non-integer coordinates U sub hat in the novel view space. And then we basically append the interpolated prediction value and the validity mask to the list of predictions for each pixel U. What we do next is we basically aggregate by minimizing the pixel-wise difference in valid pixels. This slide depicts some of the results obtained by using the fusion method just described. As one may notice, employing image-based fusion yields the most smooth result in all cases. If we would like to instead employ the multiple view consistency during training, we do virtually the same as in the previous slide, but we gotta ensure that all of the operations that we perform, that is reprojection, interpolation, and concatenation, are differentiable to be able to actually backpropagate through those operations all the way to the convolutional neural network that we are using for training. And what we do is we compute the pixel-wise difference in valid pixels, which basically expresses the multiple view consistency assumption here by computing this loss in each of the reference images, and we minimize this loss, adding that one with a small weight to all of the other losses that we're using. That might be a smoothing loss or a target loss or whatever else. Wrapping up, multiple views always provide complementary contexts, and that has been explored by numerous papers in the area of multiple view segmentation, depth fusion, and more recently in learning with multiple depth maps. So what we can do typically is we can either boost the method performance during post-processing by having the network frozen and fusing predictions in the same spatial location that are visible from different viewpoints, or we can do that during training by training with multiple view consistency assumption.